So what is cumin? Cumin is a volatile and hazardous component. Crude oil contains a small amount of cumin. Cumin has a boiling point of approximately 151 degrees Celsius and a freezing point of negative 96 degrees Celsius under normal atmospheric conditions. Cumin's molecular formula is C9H12, and the uses of cumin includes petrochemicals, plastics, automotive, construction, and also pharmaceutical industries. So how do chemical engineers produce cumin in real-life industries? Cumin is produced by the alkylation of benzene and propylene in the reactor plant. With chemical equation C6H6 plus C3H6 will produce C9H12, which is benzene. In chemical engineering realms, considering elements such as mass, volume, flow rates, molecular weight, and mole or mass fraction is needed to apply the mass balance and energy balance calculation. The cumin product flows in pipelines for transportation and storage. Its flow pattern needed to be taken into consideration to calculate the power and efficiency. Chemical engineers use Reynolds number to determine the flow pattern of cumin in pipelines. If the Reynolds number is less than 2000, it means the fluid flow with the pattern of laminar flow. And if the Reynolds number is between 2000 and 4000, the flow is transition flow. And if the Reynolds number is over 4000, it is a turbulent flow. Bernoulli equation, which established the relationship between the fluid velocity and pressure due to intermolecular forces, is closely linked to the principle of conservation of energy. And we use this particular equation for Bernoulli equation. And in Bernoulli equation, we will calculate the friction loss using this equation.
Moving on, I will be briefly explaining about the process flow diagram of cumin. Now, cumin production is achieved via alkylation of benzene and propylene following the reversible reaction. This reaction is exothermic with a heat of reaction of approximately negative 23 kilocalories per mole and typically carried out at temperatures around 300 degrees Celsius and pressures between 20 to 30 atm. The process begins with fresh benzene and propylene feed streams, which are first pressurized using a feed pump to ensure continuous flow. This pressurized feed enters a heat exchanger, where it is preheated using recovered process heat to reduce energy demand inside the reactor. The heated mixture then flows into the catalytic reactor, where benzene reacts with propylene with the presence of solid acid catalyst, mainly zeolite or aluminum chloride. Now, this reaction produces cumin as the main product with a small amount of heavy byproducts like diisopropylbenzene. The reactor effluent is then sent to a series of distillation columns for separation. First, light gases such as liquefied petroleum gas and unreacted propylene are removed in the propane tower. Next, benzene is recovered in the benzene recovery tower and recycled back to the reactor, which improves selectivity and conversion. Finally, high purity cumin is separated as the main product in the cumin tower, while heavier aromatics are removed as bottom products and flown through the IPB tower. Now, it is also taken note that isopropylbenzene is also recovered to produce maximum cumin in this plant.
Hello. So now we will take a look for the mass balance for non-reactive unit operations and also the reactive unit operations. So first we will take a look in 2.2, which is the mass balance for non-reactive system. So in this diagram, it shows the distillation column or also known as the benzene recovery tower for cumin production. So for in this feed is we have the molar flow rate given and also the 50 mole percentage of benzene, 49 mole percentage of cumin, and also 1 mole percentage of heavies. So for the top product, this is where the benzene separation occurs. So we will have 99 mole percentage of benzene and 1 mole percentage of cumin. And also the bottom product is we don't know the value for the molar flow rate, and also we don't know the mole percentage for the components that are involved. So these are the assumptions for this non-reactive system. So now next is we have 5 unknown based on this diagram, but we also have 5 independent equations. So by using the degree of freedom, the unknown minus the independent equation, so 5 minus 5, we will get 0, which means that this system is solvable. So with that, we can obtain the molar flow rate and also the mole fraction based on the values given. So in this next slide, so in this right side of the slide is the calculations that can be obtained by using the values given in order to get the molar flow rate and also the mole fraction, and we can also obtain the mass flow rate and also the mass fraction, and these are the calculations on how we can get these values. So now moving on, we have 2.3, which is the mass balance for reactive system. So in this feed is we have the reactor column, also known as the alkylation for cumin production. So in this feed is we have the benzene in, and also the propylene, and we also have the molar flow rate, which is already given. And we also have product, which is benzene out, propylene out, cumin out, and also heavies out. So these are the assumptions for this reactive system. And also we have two reactions, which is the main reaction, also the side reaction. So for the heavies, we also called we also call them as DIPB, or also known as diisopropylbenzene. So now next is we can obtain the molar flow rate and also the mole fraction based on the values given. So in the right side of this slide is the calculations on how we can obtain these values. So we can also obtain the mass flow rate and also the mass fraction based on the values given. And again, the calculations are in the right side of this slide, where we can refer to lah in order to obtain the mass flow rate and also the mass fraction. So that's all from me. Thank you.
Following the mass balance, I will now cover the energy balance, starting with section 2.4, our non-reactive benzene recovery tower. As shown in the diagram, feed enters at 100 degrees Celsius, with products existing at 85 and 150 degrees. Assuming an open, continuous steady-state system, since there are no moving parts or elevation changes, we can eliminate kinetic energy, potential energy, and shelf work. Hence, our energy balance can be simplified to the change in enthalpy equals the heat transfer, Q. Because this is non-reactive, the energy transfer is purely sensible heat. We found the specific enthalpy for each component by integrating the liquid heat capacity from our 25-degree reference state, as shown here. Multiplying this by our molar flow rate gives the total enthalpy. Subtracting the inlet from the outlet enthalpy gives us a final Q of 944,191 kilojoules per hour. This positive value means the process is endothermic, and our system must continuously supply this exact thermal energy to vaporize the benzene. Moving on to section 2.5, the alkylation reactor. This is a reactive system where chemical bonds break and form in vapor phase. Our fluid enters at 250 degrees Celsius and exits at 350 degrees Celsius, maintained at 25 atm. Using the same steady state assumption, we set up our input and output enthalpy table as shown below. First, we calculated the sensible heat by integrating specific vapor phase heat capacity from our 25-degree reference point, filling our table out. Next, we calculated the chemical heat. Using mass balance data, we can find the extent of reaction. And applying Hess law, we can determine the extended heat of reaction. Both reactions are highly exothermic, releasing about 99 kilojoules per mole. Finally, our total heat, Q, is the reaction heat plus product sensible heat minus the fixed sensible heat. Plugging in our values yields a final Q of negative 5.96 million kilojoules per hour. This shows the reactor is losing massive amounts of heat to surrounding. And that's all, and that's covered the energy balance. And now I will pass the floor to my teammates.
Now we will move on to chemical engineering fluid mechanics, which is part 3. 3.1 focuses on the layout of the piping system, and here there are several pipe specifications using different internal diameter measurements and different lengths. The piping network is designed to safely transport both reactants and products between unit operations, and different diameters and lengths were determined, and fittings such as 90-degree elbows, control valves, gate valves, and check valves were included in the layout. These fittings contribute to minor losses, while pipe length contribute to major friction losses. For ease of calculation, several assumptions were made. The flow is steady and incompressible, and friction factor of 0.02 is used for turbulent flow. And different pipe measurements were also made accordingly, varying from 1 inch to 3 inches, depending on flow rate and fluid properties to control velocity and minimize friction losses. The viscosity of propylene and benzene were also taken according at 25 degrees Celsius. Besides that, all pipelines use stainless steel Schedule 40 pipes due to their corrosion resistance and mechanical strength. Next, work and change in velocity is 0, and pump efficiency is taken as 8 kilowatts with 75% efficiency for all centrifugal pipes used in P1, P2, P3, and P5. Lastly, different lengths of pipes were also kept minimal to reduce friction loss. So for pressure drop calculation, we use the Bernoulli equation, and we will go through P1 calculation to understand these 10 steps. For the first step, the values and assumptions were determined. And then mass and volumetric flow rate was calculated. For step 4, we also calculate the average velocity. And step 5, we calculate the Reynolds number to determine the type of flow, which in this case is turbulent. Using the pipe roughness and fittings data, the total friction factor head loss was determined. In this case, pump work per unit mass is also calculated since we are calculating for P1. For step 9, we apply Bernoulli equation, including pump work and friction losses, and pressure drop across P1 was calculated to be 2,408 kilopascal. Finally, the same steps to utilizing Bernoulli's equation was used in other pipes, and this concludes us to the summary table of pressure drops comparing all pipelines from P1 to P8, allowing identification of lines with the highest loss.
There are four main steps to construct a strategy to deliver our main product, which is cumene. The first step is to identify cumene's properties. Second step is to choose suitable pipeline characteristic. The third step is to calculate daily mass and volume of cumene producible. And the last step is to design a tank for the storage of cumene. The first step is to identify cumene's properties. Cumene is a colorless liquid that has the viscosity of 0.737 millipascal second at 25 degrees Celsius and has the specific gravity of 0.862 at 20 degrees Celsius over 4 degrees Celsius. The second step is to choose suitable pipeline characteristic. We decided to choose rough pipe with internal diameter of 3 inches according to Schedule 40 table. And for the material of the pipe, we decided to choose stainless steel pipe. The third step is to calculate daily mass and volume of cumene producible. We use mass flow rate and volumetric flow rate formula, and we will get daily mass of 299,467.2 kg per day of cumene, and the daily volume of cumene producible is 347.41 meter cube per day. Last step is to design a tank for the storage of cumene. We choose polyethylene as the material of the cylindrical shaped tank. The type of roof that will be used is fixed cone roof with additional internal floating roof. For the dimensions, the tank will have internal diameter of 16 meter and height of 10 meter. The storage that will design will have maximum capacity of 2000 meter cube for 5 to 7 day operation. In conclusion, this assignment combined fluid mechanics and chemical engineering principles to optimize piping layouts and equipment selection. We achieved rigorous mass and energy balances, targeting 98% of propylene conversion and 95% of benzene recovery. We utilized Bernoulli's equation and degree of freedom analysis to eliminate bottlenecks and optimize selectivity towards cumene. We achieved to implement stainless steel construction and thermal management for high pressure and high temperature operation.